Okay, so we'll start the class now. So yesterday's class we started discussion about the springs. So in that first we see what is the definition for a spring. Spring is nothing but an elastic member, elastic machine element which is to take force and under the action of force it will deflect. When the load is removed or when the force is removed, it will regain its original shape. And after that, we are seeing what are different functions or what are the important functions of a spring and their applications also. So generally, springs are used in shock absorbers to mitigate the vibrations, and also springs are used to store the energy, and also the third applications are springs are used to measure the force as well as to control the motion. The springs are used. So we discussed these applications, and after that we are seeing different types of springs. So generally, depending upon the shape and application type of load application, the springs are different types: helical springs, conical spring, torsion spring, and leaf springs. Finally, have disc or bell-level springs. So then after that we discussed about the helical springs, and we discussed about conical springs, then torsion spring and their applications, leaf springs and laminated springs, and finally we discussed about this bell level springs also. So next comes what type of materials can be used for the springs. So spring materials. So what kind of spring materials or what kind of materials can be used to manufacture or to prepare spring. So coming back to the definition of the spring here, the spring should elongate upon the application of the load, and then when the load is removed it has to regain its shape. That means so it should have sufficient ductility. The sufficient ductility. Not only that, so if you take some applications where the load is acting on the spring, it may be steady load, or most of the cases the load is going to be a fluctuating load or a fatigue load. So when the component is subjected to a fatigue or fluctuating load, it should have sufficient toughness. It should have sufficient toughness so that it can withstand for the rated life. Let us say if I say the life of the spring is some 1 year, so generally we won't say in a year, we'll say number of load cycles, 1000 cycles or 1 lakh 10 power 6 cycles, something like that. In order to withstand that load cycle, we should have sufficient toughness. So these are the two important properties required for material which is used to manufacture springs. So a spring should have high yield strength and low modulus of velocity so that they do not permanently deform under the applied load. So like we have already said, so whenever the load is removed, it has to regain its original shape. So that means it cannot deform permanently. If it is deformed permanently upon the application of the load, if you remove the load, it still remains in the deformed shape only. It won't regain its shape. So that is not the important characteristics of a spring material. So it should possess. So in order to possess that elasticity, sufficient elasticity, so it should have a low modulus of velocity and high yield strength. Why you require high yield strength? So when you say it is going to deform permanently, if the stress in the spring materials exceeds yield strength, if it is go beyond the yield strength, then only yielding will take place. The yielding is nothing but the permanent deformation. So if the yield strength is high, so therefore the spring cannot deform permanently under the given load. Then the next characteristic requirement is low modulus. So what it indicates? Low modulus in the sense for a given load, P modulus means elastic modulus or shear modulus. You can say shear modulus or elastic modulus, Young's modulus, that is E. Shear modulus is G. If these are low, obviously our delta is high. So that means these two are inversely proportional. These two are inversely proportional. Or I can say that if E is more, you can say the stiffness is more. If the stiffness is more or if the stiffness is high, then deflection will be low. But here, if you take a reverse way, that is low modulus, that means modulus is low in the sense deflection is going to be high. So therefore, it will satisfy the condition. So if the deflection is high under a given load, so that we can avoid this permanent deformation, so that the spring can regain its shape after removal of the load. So therefore, the first important characteristics for the spring materials is it should possess a high yield strength and low modulus. That is one of the property the spring material should possess. Then second one is springs are made of material that can be formed. So but generally the springs are nothing but we discussed in the previous class. So spring is nothing but helical spring. For example, if you take a helical spring is nothing but if you take a wire of circular cross section and if it is wound in the form of a helix, we will get a helical spring. So that means here those wires are there. What are the wires which are used to manufacture or to produce the springs? Those wires are produced by forming process. Either it may be a rolling or it may be a cold run process. So that is the procedure through which the springs are spring material or spring wires are manufactured to a high strength. So that can be formed to have high strength and retain enough ductility to form, or the alloys that can be heat treated to high strength and ductility or after forming. So this is what I already told. So the spring material should have enough ductility. If it is don't have the ductility, so then it is going to break. So suppose if the spring material is having a brittle characteristics, since it is subjected to a fluctuating load, it is going to fail very easily, or maybe with less life. The spring will have very less life if it don't possess the required ductility. So therefore, since here the spring formation is or spring manufacturing is either to rolling or cold run or hot run process, so those processes will reduce the brittleness. So therefore, to reduce the brittleness, some kind of heat treatment process can be done to the spring wire so that it should possess the required the ductility. So that's what the statement will says that springs are made of materials that can be formed to high strength and retain enough ductility to form. So that means, so you can go for the material which is either cold run or hot rolled or cold rolled also here. So to a high strength and it should possess the enough ductility. Or else sometimes alloys also can be used and these alloys can be heat treated to the high strength and ductility. So that means through that heat treatment process, the material of the spring may be made to have high strength as well as the enough ductility. So before or after forming. So after forming process or before a forming process, the spring material should possess high strength and the required ductility. Both cold and hot working processes are used to manufacture the springs. So like already written here, so both either cold rolling or hot rolling or cold run process or hot run process, using that the spring wires are manufactured. The selection of process depends upon the size of the material, spring index and properties desired. So that means what type of manufacturing method used to produce the springs will depend upon these factors. One is the size of the material, then spring index required. We will see what is the spring index. Spring index while going into the terminology of the springs. There we'll see this is the spring, what is spring index, and also the properties desired or the desired properties. So based on these three parameters, the type of process will be chosen so that the spring can be manufactured. The binding of the spring induces residual stresses due to bending, which are released with the help of heat treatment. So, like we already said, in case of these helical springs, so in case of these helical springs, you will take a straight wire and it will be wound in the form of a helix. So that wounding process or the binding process will induce a residual stress in the spring. So that means residual stress in the sense before applying the load to the spring. So still there are some stresses which are developed in the spring because of this binding process. So therefore, those if those stresses are still present in the spring, then what happens is the load carrying capacity of the spring will decrease. So therefore, to eliminate or to relieve the spring from this residual stresses, so again some kind of heat treatment process should be carried out on the spring so that these residual stresses can be eliminated or relieved from the material of the spring. So then, finally, the materials used for springs are plain carbon steels, alloy steels, and also sometimes non-ferrous materials like phosphorus bronze, spring brass, beryllium, copper, and various nickel alloys. So again, depending upon how much ductility they will possess, or depending upon the requirement, these requirements, yield strength and ductility. So depending upon the application, so these are the different materials which are can be used for preparation of the springs. Either there may be either plain carbon steels or alloy steels. So most of the cases only either plain carbon steels or alloy steels are used for the springs. But in some applications, even non-ferrous materials like phosphorus bronze, spring bronze, and beryllium, copper, and various nickel alloys. So wherever you want more damping in the system. So here the spring brass, beryllium, copper or copper beryllium, and nickel alloys. These will provide some amount of damping also, not only springiness, they will provide some amount of damping also. That means damping is nothing but energy absorbing and dissipating. So that characteristics we call it as a damping. So these material will possess the damping also. So therefore, in case of in case of applications where you want to mitigate the vibration amplitudes, so people may go for these type of materials also. Okay, so broadly this is about the spring materials. So if I want to what I can say conclude about the spring materials, the requirement for any spring material is it should possess yield strength and low modulus so that it cannot deform permanently under the application of the load, and also spring should have sufficient ductility so that it can withstand the fluctuating loads. So then, depending upon the process, what type of process you are selected for producing the springs, so again that process will depend upon the type of material, size of the material, spring index, and the properties, required properties or desired properties. So then these are the majorly used materials for spring applications. They are plain carbon steels, alloy steels, and non-ferrous metals like copper beryllium, spring brass, and phosphorus bronze are also used in preparation of the springs. Then we'll come to the terminology of helical springs. So here, even though we are discussing largely about helical compression springs, this terminology is applicable for tension springs also. Most of our discussions will talk about helical compression springs, but these are applicable for tension tension springs also. Okay, so now this picture will show you the cut section of that helical spring, especially it is helical compression spring. So in this diagram you can see different parameters you can see here. One is D, capital D, then DI, DO, small d, P, of course you have a free length here. So we'll see what are these all these parameters. So before that here, this is the line what you can see. This is line we'll call it as the axis of the spring. Axis of the spring. So these diameters are measured with respect to this axis. So those diameters are D, DI and DO. So then I can say if this is a DI, then this distance from axis to this one, it is, I can call it as RI, and this is RO, and this is R. So in that, this DI is known as inside diameter of the spring. So DI is, okay, anyway I'll show it here. The main dimensions of the helical spring subjected to compressive forces are shown in figure. Like I already mentioned, even though we are discussing about only spring which is subjected to a compressive force, these parameters are applicable for even tension spring also. First one, D, the small d. So small d is nothing but, if I cut the spring here, this is the cross section of the spring wire. So which is a circular cross section here, and the diameter of that wire we'll call it as, we denote it as by small d. So therefore small d is wire diameter of the spring, which is expressed in mm. Then di, d suffix I is nothing but inside diameter of the spring coil. So this is di, inside diameter. So if I take coil diameter to or something like this, so I can say here this is di, this distance is di. Then do is outside diameter, or else if I write the outer line, so this is the outside diameter. So now if I want to relate this do, di and the small d, how I can relate that? So here you can say, you can write this do as, this is your do, so that is this one, this distance plus this distance plus this distance. So now we know this is di, inside diameter. Then what is this? This is coil diameter d, and this is also coil diameter d. So therefore I can write do as di plus 2 times wire diameter or coil diameter. We'll call it as wire diameter or wire diameter, let's say wire diameter 2d. So di plus 2d will give you d naught. So then this is the one relation you can, from this configuration diagram you can write it. And then if you want to write the expression for this d, what is the d here? So that is nothing but the mean diameter. We'll call this d is mean diameter, which is nothing but the average of your d naught and di. So you can see that exactly at the center it is drawn it here. So it is going to be d is going to be the mean coil diameter, which is also expressed in mm. And if you write the mathematical expression for that in terms of di and d naught, it is d is equal to d naught plus di by 2. The same thing I can express in other way also. So how I can write it here? D, your di plus d also I can write it as mean diameter, or capital D should be equal to di plus d. How I can write that one? Here you can see it here. So you can substitute for this d naught. So d naught we written as d naught is equal to di plus 2d. If I substitute that one to here for d naught, so then what I can write? D naught is nothing but di plus 2d plus di divided by 2. So di it is 2 capital Di plus 2 small di. So if you simplify this, we are going to get only this one. Your d is di plus small d. So that is inside diameter of the spring plus Y diameter will also give you an expression for the mean coil diameter. So depending upon the situation, maybe in some problems they make you both DO and DI. In some problems they make you DI and D, or in some problems they make you D. So depending upon that, you need to use these relations. So that means, suppose if I know the DI value and D value, if I want to calculate D, then I have to use this relation DI plus D. If I know D naught and DI, then no issue. So I can use this relation like that. So depending upon the data available in the problem, if you want to calculate, generally all our design calculations are in terms of mean diameter only or mean coil diameter only. So you need to first find what is this D. So for that, you need to look into what is the data available with respect to the given spring. So then based on that, you have to select your relation, whether you have to use this relation or this relation. Or sometimes they'll give you DA and D, they will ask find out what is D naught. Like that also in 1 mark or 2 mark question, they may ask like that also. So you need to calculate, you need to use this relation for that. So that will get, all these things will get from the configuration of the spring. Okay, right. So therefore mean coil diameter is denoted by capital D and is given by average of outside diameter and inside diameter. Okay, so you have to calculate based on the given data, you need to compute the mean coil diameter. Then the next parameter. So that means we have seen what is small d. Small d is nothing but wire diameter of the spring, and di, d suffix I, it is inside diameter of the spring coil. Do, outside diameter of the spring coil. D is mean diameter of the spring coil or spring, generally we will call it as spring or spring coil, it doesn't matter, both are same. All these are expressed in mm only. So and you have a relation between d naught and di, or something like d naught plus di by 2 or di plus small d, like that you can derive remaining expressions also. Then the next important parameter for the spring is spring index. Like already told in the previous case while discussing about the spring materials. So depending while selecting the process for the manufacturing of the spring, this spring index will plays a vital role. That means based on the spring index required, so then the manufacturing process will be selected. So then before okay, for that first we should know what is the spring index. The spring index is nothing but it is a ratio of two diameters. Those two diameters are mean diameter or mean coil diameter divided by wire diameter. We denote that one as spring index. So spring index is nothing but the ratio of mean coil diameter to the wire diameter. Spring index is defined as the ratio of mean coil diameter to wire diameter. It is denoted by capital C and is given by capital D by small d. So this capital D by small d will call it as spring index. So ratio of two diameters here, D is mean coil diameter and the small d is wire diameter. So depending upon the C value, this is ratio, then we already discussed that the type of manufacturing process will be decided. So therefore, so then how it plays the role in that. So then if the C value is less, what is its implications? If C is very high, that is spring index is very high, what are the implications? That we'll see in the next slide. So now coming to the spring index, in design of helical springs, the designer should use good judgment in assuming the value of the spring index. The spring index indicates the relative sharpness of the curvature of the coil. So here it will indicate the curvature. Curvature in the sense we are wounding the spring in the form of a helix. So because of that, some sort of curvature will be created in the spring. So how sharp this curvature that will depends upon the spring index. That means the ratio of these two diameters, that is mean coil diameter to the wire diameter. Suppose if the spring index is less, a low spring index means high sharpness. So while say high sharpness, low spring index means what is the case we are going to get? So C is less than 3 means your D is less than, capital D is less than 3 times D. So that means here, if I take this one, this is our D. Then if I go to something like this, if this D here it is 3D. So 3D means 3 times D approximately it goes to something like this. Then this is going to be very small. So then the remaining recess distance is very small. So that will create you a high sharpness of curvature. So when the spring index is very low, that is generally less than 3, when the curvature sharpness of the curvature is high, then there is a high stress concentration will be developed in the spring. Due to that, the actual stresses in the wires are excessive due to curvature effect. So that means due to this high sharpness in the curvature, the induced stresses are very high. So therefore, one has to choose the spring index wisely such that the stresses due to this curvature effect can be decreased or maybe eliminated. So for that, C cannot be less than 3. So C cannot be less than 3. So that means always you have to take C is more than 3. And similarly, at the same time, if I go for high spring index, and also not only that, if you take less spring index, so that means your diameter D by D, this D by D is less than 3 means, so this diameter and this diameter only 3 times are there, bending the wire in the form of helix is going to be very difficult thing. So therefore, the manufacturing of the spring is going to be difficult. So such spring is difficult to manufacture, and a special care is in cooling is required to avoid cracking in some ways, because your curvature is sharp here, sharp curvature is there. So therefore, there is a possibility of cracks generation in the spring also. To avoid that cracks formation, additional cooling process is required for this. So therefore, always it is difficult to produce or to manufacture a spring which is having a spring index less than 3. In the other side, when the spring index is very high, that is when C is more than 15, it results in large variation in the coil diameter. So C is 15 means your D by D is greater than 15 means you can say your D is greater than 15 times small d. Your capital D is greater than 15 times small d, which will result in large variation in the coil diameter. So if you compare this D to this P, there is a large variation. Such a spring is prone to buckling. So that means if C is more than this, so the spring can buckle, and also it tangles easily during handling. So and also it may tangles easily while handling also. So that means you cannot use C which is more than 15 also. So the problem with that spring which is having a spring index of more than 15 is it is easily buckled. The spring is going to buckle under very small load. So therefore spring index cannot be used more than 15 for any spring. Then the practical thing, or a spring index ranging from 4 to 12 is considered best from the manufacturing considerations. So here what we already seen it here. See here, when some spring index is less than 3, it is difficult to manufacture. So that means you have to choose spring index is more than 3, and also when the spring index is more than 15, then the problem with that is it can easily tangles during handling. So therefore, it should not be greater than 15. So therefore, the best possible, best values or best range for the spring index is 4 to 12 for manufacturing considerations. From manufacturing point of view, the best spring index range is 4 to 12. And then therefore some practical applications are also there. The spring index usually varies from 4 to 12. But however, spring index in the range of 6 to 9 is still preferred, particularly for a closed overrun springs, those subjected to cycling loadings. So when the load is when the load is a static load or a steady load, so the spring index can be chosen as 4 to 12. But if the load is cyclic in nature, then the range of the spring index is 6 to 9 only. So this is the preferred range for the spring index when it is subjected to a cyclic loading. So this is about spring index. So in spring index is nothing but it is a ratio of mean coil diameter to wire diameter, and when the spring index is very low, so then it will create a high sharpness of the curvature in the spring. Due to that, there is a stress concentration will be there in the spring, which will produce higher stresses than actual or nominal stresses. So therefore, a low spring index cannot be used, or low spring index is not recommended in case of the springs, especially when the spring index is less than 3 is not recommended in manufacturing point of view also. Whereas if the spring index is too high, that is when it is more than 15, then there is a possibility of the spring buckling under even small load. If you apply a very small load to the spring, it is going to buckle. So therefore, to avoid that, the spring index cannot be more than 15. So, and the usual range or the best range for the spring index for a manufacturing from the manufacturing point of view is 4 to 12 when the load is a steady load. So if the load is a cyclic load or a fatigue load, the best range for the spring index is 6 to 9. So these points we need to remember while designing the springs. While designing the springs in the problems, you have to see whether the load is steady load or fatigue load. Then, so they may not give. They will give the data and they will ask you to design the spring for this application like that. So then you have to choose your spring index. So for that, these are the points you need to remember. So generally, when the load is steady load or static load, you have to choose your spring index between 4 and 12. When the load is a fatigue load, you have to choose between 6 and 9. You need to remember these points. Okay. So then continuation of this terminology of helical springs. So next we are saying what is mean coil diameter, what is spring index, what is wire diameter. Similarly, DO and DI, that is inside and outside diameters of the spring. Then the next thing is solid length. Next terminology is solid length. So now here you can see 3 pictures here. The same spring with the different lengths you can see here. This length is marked as a solid length. This length is marked as a compressive length, and this length is free length. So that means the length of the spring when there is no load on the spring. The length of the spring when there is no load on the spring, we'll call that one as a free length. So that means, so here there is no load acting on the spring, so then whatever may be the length, that is the distance between the top coil to the bottom coil. So we'll call that one as free length of the spring. Then if I apply the load, so that is some maximum load. If I apply P max to this, the maximum load to the springs, then what happens is if I apply a compressive force to the spring is going to compress here. So therefore, if I apply the maximum load, that means the maximum possible compression in the spring, so then that length corresponding to this compression length. So here the length of the compression is delta. This is the free length. So now we are applying a force to the spring. So because of this force, if we increase gradually this force, the spring is going to compress. So here this much is going to be the compression of the spring. So from the free length, so this much is the compression. Then the remaining length, what we'll call it as the compression length of the spring. So that means if you want to relate these two, free length and compression length, your free length should be equal to this delta compression length, delta plus this compression length. So this is the compression length plus this delta will give you the free length. So that means free length is nothing but as a combination of delta plus Pmax. Combination of delta plus this compression length. Then coming to this here, see here, even in the compression position, if the here in this the spring is in the compression position, but still there is some gap between the adjacent coils here. This, if I take this coil and this coil, still they are not in touch with each other. They are not in touch with each other. So therefore, the gap is existing between two adjacent coils. If you take any two adjacent coils here, there is a gap is here. So now, if I further increase the load such that, or if I further compress the spring such that this gap is completely closed. So now you can see it here. So all the coils are in touch with this, the adjacent coil. So that means there is no gap at all. So that means it is the maximum possible compression for the spring. So that means beyond this point, the spring cannot be further compressed. So then the length at the maximum compression in the spring will give you the solid length. The solid length is going to be the maximum compression, or I can say that all the coils are in touch with each other, with the adjacent coils. So then that length we'll call it as solid length. Okay, so now we'll see the definitions. These are the three lengths. Free length, we'll use three different lengths: free length, compression length, and solid length. So and also we'll try to relate what is the relation between these three. So here it is straightforward. Solid length is nothing but if I have n number of coils. So if n is n or nt, will take nt into this diameter of d. So because each coil is in touch with each other, so therefore number of coils multiplied by the diameter will give you the solid length. Then here from the solid length here, if I am able to calculate this gap for each adjacent coils, so number of gaps here multiplied by this gap for each adjacent coil will give you the distance here, this distance plus the solid length will give you the compression length. Then that solid length plus gap allowance for each one set of coil multiplied by the number of sets plus this delta will give you the free length. So like that you can derive the relation between these three lengths. So first one is solid length is defined as the axial length of the spring. Of course, this is the axial length only we are measuring. All these three lengths are measured along the axis only. So along the axis only, that's why it is called axial length of the spring, which is so compressed that adjacent coils touch each other. That's what I already said. In case of solid length, the adjacent coils will touch each other. So in this case, the spring is completely compressed and no further compression is possible. See, because the adjacent coils are touching each other, so now it is not possible to compress it further. No further compression is possible. So then at that state, when no further compression is not possible, then at that state, if you measure the length of the or axial length of the spring, that is we call it as solid length of the spring, and it is given by nt into d, where nt is number of coils, total number of coils. Total number of coils means one circle. One circle we'll call it as one coil, multiplied by this diameter. Diameter is nothing but y diameter. You get the solid length. So where nd is total number of coils and d is the y diameter, that we know that. So that means you can, if you want to calculate the solid length, what you have to do is you need to count what are the total number of coils and you need to multiply that one by y diameter, you get the solid length. Then compression length. Compression length is defined as the axial length of the spring which is subjected to maximum compressive force. So here, that's why I showed it here, P max. So therefore, if you apply P max here, see you can see here not to compress spring for its solid length. Here this P should be greater than this P max. Don't confuse with these terms here. So, but here this is the maximum possible compression allowed in the spring. That is for maximum allowable load P max without permanent deformation. So then the length of the spring in the compressed state when P max is applied to the spring, then that length we will call it as a compressed length. Compressed length is defined as the axial length of the spring which is subjected to maximum compressive force. In this case, the spring is subjected to maximum deflection delta. The deflection is maximum in case of the compression length. When the spring is subjected to maximum force, there should be some gap or clearance between the adjacent coils. Like already told, there is a gap here in the adjacent coils. So here, this gap we call it as a clash allowance. This gap is essential to prevent clashing of the coils. That means clashing means one coil is penetrating into the other coil, we call it as a clashing. So to avoid that clashing, this gap is very essential. So therefore, if you want to write an expression for the compression length of the spring, you can write it as solid length plus this one, that is what you can call it as, if you take the clash alliance or gap here, gap between the adjacent coils multiplied by the number of coils, you will get that compression length. So generally this gap, this axial gap is going to be 15% of this maximum deflection. Generally the clash alliance or the total gap is usually taken as 15% of maximum deflection. Here the maximum deflection is delta. So because why I call it as a maximum deflection? Because I am applying the maximum load. So the deflection corresponding to the maximum load, I will call it as maximum deflection. So then, if I know this maximum deflection, 15% of this maximum deflection will be taken as the total clash allowance. So therefore, you can write the total number of gaps here. So here, NT minus 1 are going to be the total number of gaps multiplied by gap between the adjacent coils. So this gap we are taking it as 15% of this delta. So that is the compression length or expression for the compression length. So once you know that, the total gap plus this solid length will give you the compression length. Then finally you have free length. Free length is defined as the axial length of the unloaded helical compression spring. Like I already said, there is no load. So there is no load. Then in this case, no external force acts on the spring. Free length is an important dimension in the spring design and manufacturing. It is the length of the spring in free condition prior to assembly. Before taking to the assembly, that is the free length of the spring. We'll call it as a free length. That means when there is no load on the spring, the axial distance between the top coil to the bottom coil, we call it as a free length. Now, if I want to relate all these three in a mathematical form, your free length is nothing but this compression length. This is the compression length plus delta. This delta. So that is going to be your free length. But again, this compression length I can write it as solid length plus total gap. So this solid length plus the total gap between the adjacent coils, I get this one. This is going to be the total gap. So therefore, your solid length plus total gap will give you the compression length, and this compression length plus delta will give you the free length. So like this, you can relate all these three lengths, that is solid length, free length, and as well as compression length. Okay, then you can see that one more parameter, that is P. Here you can see all the diagrams, even earlier diagrams also we are showing this one as P. This P we call it as a pitch, and denoted by small p. The pitch of the coil is defined as the axial distance between the adjacent coils in uncompressed state of the spring. That means when the spring is having its free length, then if you measure the axial distance between two adjacent coils, then that distance we call it as the pitch of the coil, and it is denoted by P. So, and it is given by free length divided by NT minus 1, where NT is the total number of coils. Because you are taking a pair, you need to take it as NT minus 1. So, free length divided by NT minus 1 will give you the pitch of the spring. Then you have another term which we already discussed, the stiffness of the spring. Stiffness of the spring is defined as force required to produce unit deflection. So therefore K is denoted by P, K equal to P by delta, where P is the applied load and D is the delta. Delta is the deflection in the spring. So P by delta will give you the K. So for a linear spring, like I already told, if you draw load deflection curve, so if you take horizontal axis as a deflection and vertical axis as a load, so it is a straight line here. So that means your deflection is proportional to P. P increases, delta will also increase. P decreases, delta will decreases. And if you take slope of this curve, load deflection curve, slope of this load deflection curve will denote that one as a spring rate or spring constant or stiffness. All these three terms are same. So which is given by P by delta. So there are various names for the stiffness of the spring, such as rate of spring, gradient of spring, scale of spring, or spring constant. So all these terms are same. Rate of spring, gradient of spring, scale of spring, spring constant. All these are same. Stiffness of the spring, or sometimes we call it as rate of spring, gradient of spring, scale of spring, simply spring constant. So like all these names are same, but most probably will use spring constant and stiffness. Maybe in some cases will say spring rate. Spring rate of spring or spring rate, both are same. So like this, we can call the stiffness in a different names like this. The stiffness of the spring represents the slope of the load deflection line. Like I already showed it to you, if you draw a curve between load versus deflection, then the slope of this line is nothing but the stiffness of the spring. Then, okay, so I said earlier, while calculating the pitch of the coil, we have taken NT. NT we are calling it as total number of coils. So this total number of coils will constitute two types of coils. Again, they are active coils plus inactive coils. The total number of coils is the summation of active and inactive coils. Then how we can count how many number of active coils are there, how many number of inactive coils are there in a spring. So for that, he has given the definition for this active coils and inactive coils. When I say a coil is inactive, when I say the coil is active coil. Active coils are the coils in the spring which contributes to the spring action. Active in the sense when if I apply the load to the spring, if they deflect, then I can say it is an active coil. So that means it will contribute towards the spring action. The active coil will contribute towards the spring action. Spring action is nothing but if I apply the load, it will compress. If I apply compressive load, it will compress. If I release the load, it will come back to its original shape. So then I can say it is active because upon the application of the load, it is acting. It is activating. So therefore, we call it as active coils. So these active coils only will support your external load. That means if I apply the load to a spring, some of the coils they may not deflect or they may not activate. So therefore those coils we call it as inactive coils. So then if you want to count the number of active and inactive coils, the criteria is you need to look at into the spring where the deflection is there in the spring. You need to count all those springs. Those springs we call it as active coils. Otherwise, it is a inactive coil. So the active coils in the spring, which contributes to the spring action, support the actional force and deflect under the action of the force. So you need to look at into these three things. That is whether the coil is deflecting or not under the action of the actional force. So then we can say it is an active coil. Whereas in case of inactive coil, a portion of end coils Especially the inactive coils are generally they are end coils only, which is in contact with the seat. So that means where you are placing the spring. So this top coil or bottom coil, they are in contact with the seat, or they are in contact in the seat. So that means they cannot deflect. So does not, that means they does not contribute towards the spring action. So therefore they are called inactive coils. So based on the type of ends, that we'll see in the next slides. In the coming slides, we'll see that. So based on the type of end conditions you have, so your inactive coils, number of inactive coils will vary. So that we'll see how we can count the number of inactive coils in the spring based on different end preparations. That we'll see in the next slide. These coils do not support the load and do not deflect under the action of the external force. That means the inactive coils won't take any load, means they are not going to deflect. If there is a load, if they take load, definitely the function of the spring is it has to deflect. If you apply a load to the spring, it has to deflect. If it is not deflecting, means it is not an active spring, active coil. So therefore, they won't contribute towards the load carrying capacity also. Therefore, we call those coils as a inactive coils. The number of inactive coils is given by inactive coils is nothing but you need to count what are the total number of coils minus you need to count what are the total number of active coils. This N is the total number of active coils. So therefore, total number of coils minus total number of active coils will give you the total number of inactive coils. Or simply you can say inactive coils is equal to total number of coils minus active number of coils or active coils. So you get inactive coils. So where N is the number of active coils. So like I already told, depending upon the different informations here, in conditions. I think it is 10:30, 11:30 now. Okay, we'll see this in the next class. We'll stop now today at this point. We'll continue this in the next class. I think I already placed the attendance in the classroom. Just respond to the attendance and then leave the class.